Okay, our last talk of the day before our dinner cruise is Peter Mathys will be talking about efficient band occupancy and modulation parameter detection.
Okay, I'm going to try to make this as stimulating as I can, given the late time in the day. I'm currently in two places, at the University of Colorado in Boulder, as well as at the Institute for Telecommunication Sciences during my sabbatical from the university. So what is it that we want to take a look at? We have a whole band of signals. In this particular example, it's a 3 megahertz band, which has 6 signals inside, and we would like to know what those signals are, or at least we would like to figure out to the degree that we can what's in those signals. We assume that those signals are unknown, but we have some idea from what set of signals that they could come from. What I'm showing here is just the power spectral density of the noiseless signals in that band. The origin of this question actually came from DARPA's Spectrum Collaboration Challenge, and one of the hurdles that had to be passed to take part in that was to develop a classifier that can identify the occupied range and type of 6 simultaneous non-overlapping signals within a 3 megahertz channel. In this particular presentation, I'm actually going to look at slightly different signals than what was in for the original hurdle, but I will talk about some of the signals in the hurdle at the end as well. So we were looking at BPSK, QPSK, 8PSK, 16 QAM, and analog FM signals. We could have extended it to, say, 64 QAM or so, but we just wanted to have a reasonable variety of things for the purposes of figuring out how we can find those parameters efficiently of those signals. Okay, in real life, of course, the signals are going to be noisy. So this is the same picture, or the picture of the same band and the same waveforms in it, but with noise added to them. So this is about 10 dB signal-to-noise ratio. And because the different signals are a little bit different, for some of them it might be 12 dB signal-to-noise ratios, for maybe some other ones 9 or 8, so it's just approximately 10 dB. Okay, so we are going to take a look at two methods, the conventional method, which we start out with, and then later a frequency domain method. So the conventional method, we try to find the bands and the center frequencies and extract the signals individually. So here I've been labeling those from left to right, X0, X1, up to X5. So for example, if you want to take a look at signal X5, which is on the right-hand side, and at the bottom you see the frequency in hertz. So this is probably at about 1.2 megahertz or so. So we would basically shift that down by the 1.2 megahertz by multiplying it by complex exponential. And then we would use a low-pass filter and then use that signal. And I think there is some picture for that here. So the shifting as a first thing, then the low-pass filtering. And in this particular case, we cannot just use a polyphase filter bank, because the symbol rate is supposed to be unknown. And if we want to make any determination of what the signal constellation is later, we need to have a relatively good resolution, like say 100 hertz or so resolution. So if you do a polyphase filter bank, then you get the lower sampling rate, you have less computational effort, but you also get less resolution out of the whole thing. So basically, we do the low-pass filtering, and then we take the signal in the time domain. We take magnitude squared of the signal, and this gives us spectral lines at the symbol rate of the signal. Okay, so here is an example for that signal X5, the one that was on the very right-hand side. So after taking it down to baseband and then separating it from the other signals and squaring it and taking the power spectral density, we can see two nice peaks there. Even though it is a 10 dB signal-to-noise ratio signal, the peaks are actually fairly significant, and we can operate on that. Okay, now, if you take a look at the Fourier transform, of a magnitude squared signal in the time domain, then you can actually convert that, and I'll show it quickly here. You can convert that product of the signal times its complex conjugate into a Fourier transform, or you can take the Fourier transform of that, and that converts in this way here. You take the Fourier transform of the right-hand side here first, and then you combine that with some of the stuff that you get here with the left-hand side, exchange the order of the integration, and you find that magnitude squared in the time domain corresponds to autocorrelation in the frequency domain. That's something that's very well known, and it goes back to the central idea of the Fourier transform, that a product of two waveforms, or actually a convolution of two waveforms in the time domain, gives you the product in the frequency domain. This is just a dual of it by doing the product in the time domain and then get correlation in the frequency domain. So we're going to make use of that part here in order to do our computation. And what we need to compute now, the formula down here, the integral of x of f plus nu times x star nu d nu. But because the signals are only in specific places, we don't really have to take an autocorrelation in the frequency domain over the whole band. That's what we're exploiting here, basically. We have to just take a look at where the signals are overlapping. And if you were in the talk earlier that Fred Harris gave, you know that the information about the timing, that's all in the excess bandwidth of your signal. That's not in the signal itself. Or in the part which is below half of the baud rate of the signal. So I have a second picture here that shows this more clearly. So what's grayed out in here, or slightly blued out in here, we don't have to make any computations here. We just make computations in those white portions here. And then the other key thing is to realize that we don't want to do the regular autocorrelation where we just integrate over the whole range of things. We just want to do that over each of those white spaces here individually. I call that a band-limited frequency domain correlation. So we do actually 6, in this case where we have 6 signals, we do 6 small correlations in just those portions that we are interested in. And so in this way, I can actually get parameters of the 6 signals individually without having to separate them explicitly. Okay, in the formula here, you know, the FBT, that means it's a trial baud rate. So what we're doing here is we're shifting those signals. Let's look at this one here again. The green and the red here, those are shifted versions of each other. And the shifting is by this little f in here. And we vary that f going from, if we do f0, then we're just looking at the power in the signal. If we make f equal to the baud rate of one particular signal, then if we actually do the computation here over one of those wide spaces, then we're actually getting a peak that comes from the baud rate. So we are shifting those signals with respect to each other, and for each of the shifts, we compute those individual correlations of the 6 waveforms. And if we have shifted in such a way that we have achieved the baud rate of one of the signals, then we're going to get to see a peak at that baud rate. And the others will not have a peak. And so we're doing this and actually show that in a 3-dimensional graph. And you can see here in front where you see the gray, that is the power of the signal. I have scaled that down. That would actually be larger than the rest of things in here. I've scaled it down so that it doesn't obscure the signal or the picture. And then as we go here horizontally, we have the center frequencies of the signals. And if we go in the depths here on the y-coordinates, then we have the baud rates. And at the front, baud rate would be 0, so that's why this power. And then as we go back here, for example, this one of the signal x0 has a baud rate of maybe about 50 or so kilobaud. This one here doesn't have any such thing. This one over here has a baud rate of maybe about 90 kilobaud. This one here has maybe 80 kilobaud. This one has 90 kilobaud. And the signal here doesn't have anything at all. So basically, we're looking at this three-dimensional picture, and we get to see the landscape of what's happening in the whole band. We don't have to individually compute it for each of those and separate the signals from each other. We get to see it all in one go. This is the noiseless case in order to have more clarity. If we put noise in, if you have 10 dB signal-to-noise ratio, of course you do get to see a reflection of that noise, but you can still see very well those peaks that you get at the baud rate. And the interpretation of it is that the leftmost signal, that was what I called X0, that one is a signal which has a baud rate, so that must be a digital signal. We don't know if it's a QPSK or a BPSK at this point. The next signal, which I would call X1, that doesn't have any peak at the baud rate. So that is a signal that was maybe frequency modulated. It could actually also have been a signal that has a constant envelope. Okay, that would also show up this way. And then this one here is, again, a digital signal. And this one here is probably an analog FM signal. This one is a digital signal, and this one is a digital signal. So basically, we can immediately tell here which ones are digital signals. And then comes the next step where we say, well, now, if we do want to know more about the signal, where we want to take a look at what is the signal constellation, for instance, then we're just picking that particular signal in the frequency domain in the Fourier transform that we have already made. We set everything else to 0, and then just simply shift it down to 0, all in the frequency domain. And then in the next step, we say, now we don't need a large resolution anymore because we have determined the baud rate already. So we can now go and actually focus on just this part of the Fourier transform that we need, which corresponds to doing a decimation in the time domain. And so in this particular case, we reduce the bandwidth by a factor of 10, meaning that we decimate by a factor of 10 in the time domain. So we take now the inverse Fourier transform of that lower picture here. And I should mention that I'm just showing you the magnitude of the Fourier transform here. But of course, for doing this right, you need to take both the magnitude and the phase, or the real part and the imaginary part. Okay, and then I'm using that inverse Fourier transform because I know the baud rate. I can now synchronize to the signal, and I can show where the actual best sampling points are. And you can see that this is a 16 QAM signal. You can see that on the left, which is actually the noiseless case, you still don't get to see just a single point for each of those. That comes from the fact that I was too lazy to actually put in a matched filter receiver. And if you have an RRCF, a root raised cosine signal, that of course has intersymbol interference before you go through the matched filter at the receiver. That's the whole point there. But you see here, even with a 20 dB signal-to-noise ratio, you actually still get the fairly good picture. So now, what is the advantage of this? Can we quantify this? Now, we have to be somewhat careful when we try to quantify this, because you could, of course, fudge things in many different ways. Okay, but I made some sort of assumptions to get at least some idea of what's going on here and whether that is worthwhile or not. So I'm assuming the same parameters that I have used for this example, which is that 3 megahertz bandwidth, which meant that the sampling rate was 3 megahertz. And then the frequency resolution, I assumed we need 100 hertz in order to get a reasonably good estimation of the baud rate. Needing the 100 hertz means that we have to take 10 milliseconds of the signal for the FFT. And by the way, I just used numbers that I can sort of nicely work with. Of course, if you were to implement this in a real implementation, you would probably use powers of 2 for the FFT. So because I take 10 milliseconds and the whole thing is sampled at 3 megahertz, I get an FFT block length that is 30,000. I assume the signal bandwidth of about 100 kilohertz. Some signals are a little wider, some are a little bit more narrow. And the units of measurements that I'm using is multiply, accumulate instructions. Okay, so I assume also that both of the conventional and the frequency domain method require some sort of an initial FFT of length n to estimate initially the center frequencies and the bandwidth of the signals. Okay, so now for the conventional method, we have to shift each signal to baseband, multiplying with the complex exponential here. I did not count those operations. That doesn't really use a lot of computing power. Then you need a low-pass filter for each of the signals. And that is actually turns out to be the major effort that you have to do in computation-wise. So I estimated this to be about 3.6 million multiply accumulates per signal. And then you have to square each of the signals, compute the FFT, and for each signal again, with an effort of about n times log 2n. And of course, there might be some multiplicative factor in front of that n times log 2n. But I estimated it to be about 0.45 times 10 to the 6. So altogether, if I take the 3.6 and the 0.45, I get about 4 million max per signal. In the proposed frequency domain method, I have to compute those integrations over those wide bands that I had in the frequency domain. And because I know where the center frequencies are to a fairly accurate degree, and also what possible baud rates are, I only have to vary over those parts. And so I assumed that I have to go plus minus 10% on the baud rate and plus minus 10% on the center frequency. And then I came up with about 2.4 times 10 to the 5 multiply accumulate signals per signal. Accumulates per signal. And comparing the two sides here, I get about close to 20, factor 20 improvement by using the frequency domain method as opposed to the conventional method. Okay, again, like I said, you could compute things a little different. I assumed, for example, here an FIR filter for the conventional method. You could, in principle, use an IIR filter, but that would then distort things, and that's usually not that good for digital signals. Some limitations. Like I mentioned, if you have no idea what the baud rate is and you have to determine it to a reasonable degree of accuracy, you need to have a relatively high frequency resolution if you want to later figure out what the signal constellation is. So this is different in the case where you have unknown signals from the case where you assume you know the transmitter and you just have to, you start close to what the baud rate is, and then you just have to synchronize to minor differences from it. So as an example, for a 20 megahertz frequency band, an FFT of length about 200,000 or larger would be needed, and that would be needed for either method if you want to have this 100 hertz resolution. But something that's interesting that only occurred to me while I was working on this and actually preparing the paper for the GNU Radio conference is there is a conceptual difference between the two methods. If you use the conventional method and you have your time domain signal separated or isolated from the other signals, and then you do the magnitude squaring and you look at the power spectral density of that, that is actually actively producing a peak at the place where you have the baud rate. Okay, so that comes out, and you can actually, if you have high enough resolution, you can determine the baud rate very accurately using that. If you use the frequency domain method, then you are taking those two signals, the Fourier transform and the complex conjugate of the Fourier transform, and you shift them with respect to each other, and you have to sort of determine by how much you want to shift that. And by how much the resolution by how much you can shift is given by the delta F that you have been choosing, which I chose to be 100 hertz here. So you shift that, and then you try at each of those shifts whether that band-limited correlation is going to give you a frequency a peak in the frequency domain or not. And only if you hit with your trial baud rate, if you are close enough to the actual baud rate, you're actually going to get the peak. Okay, so you try several different things, and then it just shows up that if you tried by good fortune or by thinking well, if you hit the right one, then you're going to get the peak out. So those are two different conceptual ways of looking at this. Then if you have constant envelope modulation like CPM, CPFSK, or GMSK, then you produce signals which are of the form A times e to the j 2 pi fct plus phi of t, where all the modulation is inside that phi of t, the phase basically of the modulation. Okay, so now if you take this thing here and you take magnitude squared, all you get is a squared out of it, because e to the complex exponential just has an amplitude of 1, and that's it. So we don't get any symbol rate information from that, and here's an example of a signal. That's actually one of those that was taken from the hurdle of the spectrum for the spectrum collaboration challenge. So there the signals were either analog FM, QPSK, or GMSK signals. And so in here are some of each of the type of those signals. This happened to be a signal with a signal-to-noise ratio of about 20 dB. That was just how it was generated by what DARPA gave us. And here's that three-dimensional graph that I'm producing by using the frequency domain method. And you can see here on the very left-hand side signal, what I would call X0. That doesn't really have much in the back here, but the second signal, that has a clear peak, so this one must be a digital signal and probably a QPSK signal out of the choices that we have here. The next one here just has something in front and nothing in the back, so probably this one as well as this one over here, X0 and X2, those are probably FM signals. In fact, you can see back here that there is this peak on top of it, or that spectral line on top of it. And that comes from the fact that it was an analog FM signal, and there was some music that was modulated on top of it, and the music had some pauses in between, and then you just get to see the carrier. So you can actually tell from looking at that probably those should be analog FM signals, and indeed they were. And then this one here, you can see a high peak here again at roughly about, the scale here is different from the previous figure. So this is roughly at about 100 kilowatt, and this one is at about 100 kilowatt. So those two signals are most likely QPSK signals in the given context. And the signal here, which would be X4 in the way that I'm counting this from left to right, that shows some peaks, but nothing really distinctive in there. And so that is something that needs to be evaluated more closely. So what we do is we basically take from the Fourier transform that we computed already, we just take this piece, shift it down to baseband, and then take the inverse Fourier transform. And then we take the square of that, but not the magnitude squared, because just shifting a constant envelope signal down to baseband is not going to improve anything in terms of finding the baud rate when you magnitude square it. So what we do is we just simply take the real part of that signal, so that makes it actually not a constant envelope anymore. And then we square it, and we see now those peaks at the baud rate, and then we use that to actually display the signal itself. And of course, looking at it, you can immediately see that this is a constant envelope GMSK signal in this particular case. Okay, so that's pretty much all that we have been doing. One of the main reasons why I was triggered to do this is, of course, on one hand, the spectrum collaboration challenge, but on the other hand, also working together with people that are more in computer science. What they were sort of asking is, well, how do you know those things? How do you know, for example, that the timing information for a digitally modulated signal is not in the middle of the signal, but at the edges of the signal, and things like that. And, can you give me some literature where I can read up on that? And I was trying to find something that would be sort of easy for somebody in computer science to just brush up on that and then do some things. And, I couldn't find anything. So I figured maybe I should look into this a little more deeply. And actually, it turned out it required a substantive amount of effort to just produce those figures that I've been showing you. And I decided to publish it somewhere. So here it is at the GNU Radio Conference proceedings. And I've also put the files, the Jupyter notebook that I used for making the figures and the data files that I produced for making the figures. I've been putting those onto GitHub, so you can, if for some reason you have a student that needs a little bit of occupation, you can tell them, try to reproduce that and see if it works. So with that, I guess I'll be happy to take any questions. Or, I'll be also happy to hear if somebody just finds, yeah, that's clear. Somebody did that in the 1950s, and you just didn't know about it. I was actually trying to find whether there is something around out in the literature, and with the limited amount of time that I had for searches, I couldn't find anything.
Yeah, thanks, Peter. So my question has to do with the heuristics that you kind of talked through. I've spent a lot of my career going from heuristics to algorithms, and it can be pretty tough. So do you have a feeling for the amount of intuition that you're bringing to that last discussion of how to get the baud rate and how to identify it as GMSK and so forth? That sounded relatively sophisticated. It'd be nice to have an algorithm that did that. Any thoughts on how hard that is, or on this dimension of putting into GNU radio blocks of some type?
That's a very good question. I was actually, because I submitted it to GNU Radio, I was sort of hesitant to submit it because I didn't have a GNU Radio block for it, or even that algorithm that you're looking for. I'm thinking that an algorithm would probably have to go into some FPGA or something. It requires a lot of fiddling. I mean, if we go back here to this picture, let's see, this one here. The main thing that you actually have to do is you have to, it's not too difficult to find what is the center frequency, what is the bandwidth. You set some thresholds, and in fact, that's what I did in the picture here. This one here, you can see the dashed line at the bottom, that's the threshold. And that actually comes, I wrote that you could use a Welch modified periodogram, but I actually produced that by using the frequency domain method and just using a trial baud rate of 0 so that I get the power. And so even a noisy signal is actually looking quite good in that. So I would say that it's not too difficult to find center frequency and bandwidth in an automated way. Okay, but then you have to make some decisions, I think, as you go into this phase here, where you have to say, now for each individual signal, where do I start with my baud rate trials? I think you could, again, probably just do it on the basis of some thresholds and do that. And maybe you have to go a little bit more than just the plus minus 10% that I've been talking about. In fact, to produce my graphs, I didn't bother going just over the small pieces. I just let the whole thing run over the whole frequency range. But of course, if you want to have less amount of computation. If you want to save on computation and be more efficient, then you have to actually go and exploit that. So this would probably be the hardest part, is to set those thresholds right so that you only have to go over those bands. And then once you have that, for the spectrum collaboration challenge, it was not necessary, for example, to know what the constellation is of the signals. So I just did that because I was curious for those signals. If you want to do that, then of course you now have to take the baud rate that you figured out, and you have to feed that into an actual receiver. But that's not that much different from a regular receiver for QAM16 or BPSK. You just don't know yet at the beginning which one of those it is.
Any more questions? Okay, that looks like this will conclude the program for the day. I look forward to seeing you on the boat at 6:30 and tomorrow morning for more talks.